Lab Module number 5, Thermal Analysis of Phase Diagrams. In this module, we will use thermal analysis to determine the liquidus and solidus temperatures across a series of alloys in the lead-tin binary alloy system. We will use the technique to relate the compositions of the alloys to the corresponding variations in liquidus and solidus temperatures in the phase diagram. We will be using two different thermal analysis techniques. The first one is simply measuring the cooling curve for the various samples. This is a more semi-quantitative approach. The second approach is to use a differential scanning calorimeter, a device that can provide quantitative information about thermal processes. We will be using both techniques and comparing and contrasting the results obtained from both techniques. Let's have a preliminary discussion of phase diagrams. Phase diagrams are really composition temperature roadmaps for the design of microstructures. They are incredibly effective tools that can be used to produce microstructures tailored to achieve specific properties and performance metrics. Shown here is a very simple binary phase diagram for the copper-nickel system. This type of diagram is referred to as an isomorphous binary diagram. In this type of phase diagram, copper and nickel, both metals are FCC cubic metals having atoms of nearly identical size, allowing the formation of a continuous solid solution from pure copper through pure nickel, meaning there are no other crystalline structures or phases that form between the two pure elements. This is the type of phase diagram referred to again as an isomorphous phase diagram. There exists only a single solid phase marked alpha in this diagram across the entire composition space between the two pure elements. In this diagram, you can see the melting point of pure nickel is marked at 1453 C on the right vertical axis, and copper's melting temperature of 1085 C is marked on the left axis. Above the red top curve is a region where all liquid exists, meaning the liquid is a random disordered mixture of copper and nickel atoms. The top red curve is referred to as a liquidus line, or liquidus curve. It defines the boundary between 100% liquid and some mixture of liquid and solid. The bottom red curve is referred to as a solidus line. It is the boundary between 100% solid and the two-phase region of liquid and solid. So the region enveloped by the two red curves is a two-phase region where both solid and liquid coexist in different amounts depending on composition and temperature. At the two endpoints where the two red curves converge, it's where the liquid and solid transform at a single temperature associated with the pure elements, copper and nickel. In other words, the vertical right axis is the pure nickel line, and as we cool from above the melting point through the melting point, it undergoes solidification from liquid directly into 100% solid. Solidification occurs at a single temperature where all the liquid converts to solid. Similarly, along the left vertical axis for pure copper, the same type of behavior exists above the melting temperature of pure copper liquid. Copper exists as pure liquid, and upon cooling through the melting temperature, transforms to 100% solid at that single temperature. However, in the composition range between the pure components, for example at 50% copper and 50% nickel, upon cooling from the liquid state, you enter a two-phase region where the amount of liquid is high when you cross through the liquidus curve. But as you cool vertically through this section, the amount of solid continuously increases, and eventually when you hit the solidus curve, where all the liquid is gone and 100% solid takes over. However, the transition from 100% liquid to 100% solid occurs over a range of temperatures, rather than at a single temperature the way it does for the pure elements. If we consider the solidification of a pure metal again, as heat is extracted from the molten metal, the temperature declines with time due to cooling of the liquid. When the liquid reaches the melting point of the pure metal, the temperature time plot exhibits a plateau associated with solidification, where the heat of fusion, or the heat of solidification, needs to be released to form the bonds in the solid state. It is during this plateau where the heat of fusion is released, and during which time there is no further drop in temperature until the heat of fusion is liberated. Then the solid exists, and the solid continues to cool from the melting temperature down to room temperature eventually. Now let's consider the solidification of an alloy as it passes through the two-phase liquid plus solid phase field. Take a composition in the copper-nickel binary isomorphous diagram. In this case, we've chosen a composition of 35% nickel and 65% copper. The binary liquid exists above the liquidus curve, the upper red curve. Since there's a single-phase liquid present there, the composition of the liquid is 35% nickel, 65% copper. Upon cooling, when we hit the liquidus curve, the liquid will begin to convert some liquid to solid. We can apply the lever rule here to determine the fractions of liquid and solid present. As we continue cooling down, the amount of solid will continuously increase, and the amount of liquid will continuously decrease until we reach the solidus curve, at which point all the liquid is converted to solid, and the solid will continue to cool. Since the transition between 100% liquid and 100% solid occurs over a range of temperatures, the cooling curve for an alloy of this type does not have the flat plateau or isotherm, but rather has another inclined cooling profile associated with passing through the two-phase region. Because solidification of an alloy takes place over a range of temperatures in the two-phase field, the thermal curve shows a slope change where the solidification begins and again where it ends. This marks the temperatures on the liquidus curve and the solidus curve that define the solidification start and end for a given alloy composition. For this lab, we will be studying alloys in the lead-tin binary system. This system is different than the copper-nickel system. The copper-nickel system is what we refer to as an isomorphous binary system. The lead-tin system is what's referred to as a binary eutectic system. The difference here is that there's a temperature and composition where three phases can coexist: liquid, solid alpha, and solid beta. Note this point on the phase diagram, which appears as a V created by two converging liquidus curves to an isothermal horizontal line at 183 degrees C. In this lab, we will make measurements for lead-tin alloys across the phase diagram of this binary eutectic system. In this lead-tin diagram shown here, on the right, we have 7 different samples that are from pure lead to pure tin and alloys in between. One sample, indicated as an unknown composition, is a lead-tin binary alloy, but the composition is not being revealed. It will be part of the exercise to determine the composition of that unknown alloy by the thermal analysis approach. As shown in the previous slide, there were 7 total alloy compositions, 1 unknown and 6 that are known. The 6 alloy compositions that are known are indicated by the red dotted vertical lines in this diagram. In other words, for the 6 known alloys, their compositions are represented by the vertical lines, and their solidification behavior should follow the behavior indicated in the phase diagram. In 3 of the cases, the alloys will solidify through a 2-phase alpha plus liquid region. One alloy is chosen as the eutectic composition and will pass directly through from the liquid through the invariant point of the eutectic transformation. Each end component, pure lead and pure tin, are also included. The unknown sample has a composition that lies somewhere between pure lead and pure tin, but its composition will be the task for you to determine in this lab. You have a sample of pure lead on the left side and pure tin on the right side, and then 4 alloys represented as 30, 40, 50, and 63% tin in lead. Throughout the analysis of the lead-tin binary phase diagram, you will be asked to assess phase equilibria using Gibbs phase rule, which reads that the number of phases present plus the number of degrees of freedom is equal to the number of components plus 1 when pressure is considered a constant. For example, if we apply Gibbs phase rule at the melting point of pure lead, the number of components is 1, just lead. At the melting point, 2 phases can exist, liquid or solid. It's the transition between those 2 phases, so right at the melting point, both phases can exist. If we apply Gibbs phase rule and solve for the degrees of freedom, what we find is that since P is 2 and C is 1, the right side of the equation equals 2, and since P is equal to 2, F must be equal to 0. What does it mean to have 0 degrees of freedom? It means that one cannot change the composition or the temperature and maintain that condition of 2 phases being present at that point. If we apply Gibbs phase rule, for example, at the eutectic point, the number of components is 2, lead and tin. The number of phases present is 3. There's liquid just above the eutectic point and therefore exists at the eutectic point. And you have the phases alpha, which is a lead-rich phase containing small amounts of tin, and there's beta, which is a tin-rich phase containing small amounts of lead. At the eutectic point, all 3 phases coexist. Again, when we use Gibbs phase rule, it indicates that there's 0 degrees of freedom. What does that mean? That means that if we change either composition or the temperature, then the 3 phases no longer coexist. If we apply Gibbs phase rule in the middle of the 2-phase alpha plus liquid region, then the number of components is 2, the number of phases is 2, liquid and solid, and the components lead and tin. And so when we solve Gibbs phase rule, F is equal to 1. What does that mean? 1 degree of freedom. It means that because the location lies in the 2-phase region, we can maintain the two phases present by varying either temperature or composition, meaning that I can move vertically up or horizontal from the blue point in the center of the phase diagram and still maintain two phases present. Shown here are the compositions of the samples to be tested in this lab. The samples include pure lead, lead with 30% tin, lead 60% lead, 40% tin, 50% lead, 50% tin, 37% lead, 63% tin, and then a sample of pure tin, as well as one sample that we've indicated as an unknown composition. Let's explain how the first part of the experiment is carried out and what data will be collected. To begin the cooling curve analysis, we have a software program that will record the temperature of the thermocouple that will be immersed in the crucibles of the liquid alloys and record the temperature as a function of time to produce the temperature versus time cooling curves. To begin the experiment, the crucibles are placed on a hot plate and heated high enough to convert each sample into a liquid. Then the sample is removed from the hot plate and transferred to a second station where we use an insulation brick and a mold to position and secure the crucible, and then immediately insert a thermocouple into the crucible, into the liquid metal. And then as the crucible cools, we record the temperature versus time data on the computer. Now we will show you the raw data collection for the pure lead sample. When the thermocouple is immersed into the molten lead sample, the temperature rises very rapidly to the temperature of the liquid. And then as the liquid slowly cools, the temperature drops as a function of time, producing the negative sloped curve that you see being displayed in the video. You will note in the video that as the lead cools, it eventually reaches the melting temperature of lead. The cooling curve stops going down and reaches a plateau or an isotherm. This isotherm is at the melting temperature of pure lead, where the liquid is being converted into solid. At that temperature, the liquid must transform to solid, giving up the heat of fusion. But the liberation of the heat of fusion is not instantaneous, but rather requires time. The heat of fusion must be liberated as a function of time, and so a horizontal isotherm occurs until all the heat of fusion is given up and all the liquid is now solid. At which point at 318 degrees C, and this measurement is defined as the melting temperature, slightly off the actual temperature due to the calibration of the thermocouple. The cooling of the solid then follows, and as you note, there's again a downward sloped curve. It's now more gradual than the cooling of the liquid because the solid itself cools more slowly than the liquid. Assessing the entire curve, it now consists of an initial downward negative slope of the cooling of the liquid, a short horizontal isotherm associated with the liberation of the heat of fusion, and then a downward slope of the cooling curve of the solid. And the cooling of the solid would continue along a similar slope until it reaches room temperature. We then go in sequence from one crucible to the next, each time removing it from the hot plate where the sample is molten, putting it on the fire brick so it can cool slowly, inserting a thermocouple into the liquid, and then recording the temperature versus time measured by the thermocouple in both the liquid and solid states inside the crucible. We now show you an example of the cooling curve data collection for one of the lead tin alloy samples. Again, when the thermocouple is immersed into the molten sample, the thermocouple temperature rises very rapidly, and the liquid begins to cool. We have a slow negative sloped cooling curve, and it will remain that way until we hit the liquidus temperature. At the point when we hit the liquidus temperature, the slope of the curve will change. It will decrease the slope. It will become more horizontal in the diagram, but the change will not be to the extent we had for the pure lead solidification, because now we're passing through a two-phase region of liquid and solid. It'll be at a different slope than the cooling of the liquid, but it's not an isotherm. As you will note that the temperature shown in the top of the screen in the small box, that temperature continuously decreases. You should note at this stage that the slope of the curve is starting to change. It's becoming more horizontal, but again not an isotherm. The temperature does keep dropping in the window at the top. Now, as the liquid-solid two-phase region reaches 183 degrees C, which you will recall is the eutectic temperature of the lead tin system, the sample will now reach an isotherm. This is where the liquid present has shifted its composition all the way to the eutectic composition. Now the remaining eutectic liquid must liberate the heat of fusion to transform into the two solid phase alpha and beta phase constituents below 183 degrees C. So there is an isotherm here until all the liquid that was present when we reached 183 C transforms to solid, giving up the heat of fusion of that liquid. The eutectic liquid behaves quite similar to a pure element because there's a single temperature associated now with the transformation of the eutectic liquid into the solids alpha and beta. At the point when all the heat of fusion has been liberated, as you see here now, the temperature begins to drop again, but rather slowly as this solid now continues to cool towards room temperature. Note the slight decreasing slope of the cooling curve beyond the isotherm at 183. So the cooling curves for all 6 samples associated with this lead tin alloy system, plus the cooling curve for the unknown, have been collected and stored and provided in the form of Excel files of the temperature versus time cooling curves for each of the samples. This is the data that you will do the first portion of the analysis of this report on. The second technique for measuring the thermal behavior of these alloys is to do the measurement in what's referred to as a power compensated differential scanning calorimeter, or DSC. A DSC can be used to measure many thermal properties of materials. It's often used to determine phase transition in materials, such as measuring melting points, glass transition temperatures of polymers, the enthalpy or energy absorbed when melting, the crystallization point of polymers, the energy released during crystallization. You can also measure solid state transformations and whether the transformations are endothermic or exothermic and the specific amount of heat associated with those transformations. So let's describe a power compensated DSC and how it works. In a power compensated DSC, we have 2 independent furnaces. The furnaces are embedded in a large heatsink so that their temperatures can be isolated from each other, but the 2 furnaces are controlled in an identical manner. The furnaces consist of a platinum resistance heater and a thermocouple to measure the temperature of each furnace sample. There are two control circuits, one for the average temperature control and the other for the differential temperature control. The way the equipment functions is that it tries to drive each furnace to maintain the same temperature on heating or cooling. We use one side as a reference furnace, and a reference, a known sample, or often simply an empty furnace or a furnace with a crucible, where the crucible is identical to the crucible that will be used on the sample side. In the second furnace, there's our sample of interest, contained in a crucible identical to the reference side. What we're going to do is to compare the amount of power needed to raise the temperature of the sample furnace relative to the power required to raise the temperature of the reference furnace. Because when the sample either absorbs or liberates heat at a different rate than our reference furnace, then we're going to have to increase or decrease the heating rate of that furnace. We're going to measure the difference in the temperature between the two furnaces. So again, for example, if the sample undergoes a phase change, that is perhaps an endothermic transformation, it will require additional heat or power input to keep that furnace at the same temperature as the reference furnace. We can measure that difference in heat flow. So unlike the simple cooling curve analysis we previously showed, we not only can detect the temperatures of the phase changes, but we can also then measure the power required to achieve a constant temperature between the two furnaces and use that to determine the heat associated with the phase change. So we get quantitative information about the thermodynamic properties of the phase changes. Here we show a photograph of the two furnaces located down inside of the large heatsink. One side is the reference furnace and the other is the sample furnace. So in a power compensated DSC, if the sample undergoes an endothermic reaction where it absorbs heat, or an exothermic reaction where it gives off heat, the sample furnace will require more or less energy to increase the temperature at the same rate as the reference furnace. By measuring the difference between the power applied to each heater as the temperature is increased or decreased, the energy consumed or energy given up, we can determine the amount of heat required for the transformation. On the right here, we show an example of a DSC trace involving both an endotherm and an exotherm for a material. From this curve, we can extract the onset temperature and also measure the area under the peaks to determine the amount of energy or heat associated with those phase changes. Let's look at DSC results for one of the pure elements in the lead tin system. In this case, we're going to take a sample of pure tin and show you the DSC curve associated with heating it up through its melting temperature and then cooling the liquid back down through its solidification process. The cooling curve then represents a cooling curve very similar to what we measure in the thermal analysis cooling experiment done previously, except that now we can extract the heats associated with the transformation, the area under the peaks. We can also learn something about the difference between melting and cooling in terms of the temperatures associated with that transformation. The melting temperature on the heating curve and the solidification temperature on the cooling curve are now dependent on the rate at which we are heating and cooling. If we cool or heat very slowly, then the two transformation temperatures, melting and solidification, will be nearly the same. But you need to go extremely slowly in order to achieve thermal equilibrium that allows the transformation on heating and cooling to be identical. However, in a DSC, we have the ability to extract heat at a rate or input heat at a given rate that is controlled by the furnace heating and the cooling of the furnace. So we can control the heat input and the heat extraction. As such, we can heat and cool at rates that don't achieve complete thermal equilibrium, and hence the temperature that a sample melts at and the temperature that the sample will solidify at can be different based on the rate at which we're extracting or inputting heat. In other words, it's possible to actually undercool the liquid on the cooling side, such that the solidification temperature is different than the melting temperature on the heating side. This is demonstrated in the next slide, where we now show you the actual DSC trace for the melting and solidification of pure tin. Note that the two peaks here, the endotherm and the exotherm, do not lie directly on top of each other. This is because the experiment was done at a heating and cooling rate of 40 degrees C per minute, a rather fast cooling and heating rate. This is demonstrated here by the fact that while the tin melts at its melting temperature on the heating side, we are able to achieve some degree of undercooling, meaning that we make the liquid remain liquid to a temperature below its melting temperature. In the cooling curve, the transformation temperature is suppressed relative to the melting temperature on the heating side. Now, from this data, we can also extract the melting temperature. This is done in a similar fashion to what we did previously for the TGA data for the Curie temperature measurements. We're going to use the intercept between two lines drawn tangent to the heating profile at the melting temperature. The two red lines shown here are the tangent lines, and where they intercept defines the melting temperature, here to be 231 degrees C, the melting temperature of tin. Now we consider the DSC result for the eutectic composition of 63% tin in lead. In this case, the liquid, a combination of lead and tin atoms, exists as a liquid all the way down to 183 degrees C, significantly below the melting temperature of each of the pure elements involved. So a liquid cooling through the eutectic composition reaches an invariant point where at one temperature, 183 degrees C, the liquid and two other solid phases, alpha and beta, all coexist. Three phases coexist at that temperature. However, when you think about it, this is very much like the melting of a pure element in that all the transformation from liquid to solid occurs at a single temperature. Here we show you the DSC result for the melting and solidification of the eutectic composition of lead tin. Again, you will note there's a single endotherm associated with the heating cycle, where the solid has to absorb heat in order to transform from solid to liquid. On cooling, we're able to suppress the solidification temperature and undercool the liquid so that the endotherm and exotherm do not lie directly on top of each other. But again, the only transformations are between 100% solid and 100% liquid on heating, and 100% liquid going to 100% solid on cooling, very much similar to the melting and solidification of a pure element. The only difference is that the solidification of the eutectic liquid involves the transformation to two different solids. It's worth noting that whether the initial liquid is the eutectic composition and upon cooling passes through the eutectic point, or if the composition is to the left or right of the eutectic composition, As the liquid cools through the two-phase region, the liquid composition tracks towards the eutectic composition, and eventually the liquid reaches the eutectic composition and then must undergo the same invariant reaction, transforming from liquid to the two solid phases. Now let's consider the solidification of an alloy that's off the eutectic composition, in this case to a higher lead content. As the cooling begins from the liquid state, we transition through the liquidus into a two-phase region involving liquid and solid. In this case, the solid is alpha, but because it's forming above the eutectic temperature, we refer to it as proeutectic alpha. So as we cool through the two-phase region, we begin forming proeutectic alpha, and its composition tracks along the solidus curve on the left-right curve of that two-phase region. The left red curve of that two-phase region. The liquid follows the liquidus curve, sliding down from the liquidus temperature down to the right towards the eutectic temperature. So the liquid is becoming enriched in tin as it cools. Eventually, that liquid will reach that eutectic temperature at the eutectic composition, and that remaining liquid will then transform to the alpha and beta of the two-phase region. This two-phase mixture of alpha and beta is referred to as a eutectic structure, and it's a mixture of alpha and beta that's different alpha than what formed above the eutectic temperature. So again, the alpha forming in the two-phase liquid plus alpha region is referred to as proeutectic alpha, and below the eutectic temperature it's simply alpha. Now we're showing the heating and cooling DSC data for the 60 lead 40 tin sample. In this case, you'll note that the cooling and heating curves have distinctly different shapes than for the previous pure element or eutectic composition sample. You note that on the heating, there's a change in slope on heating prior to the large peak associated with passing through the eutectic temperature. We begin to get some melting of the sample, and then all of the remnant proeutectic alpha undergoes melting, resulting in that large endotherm. So in this case, the sample doesn't entirely melt at a single temperature. This is perhaps easier to observe when we look at the cooling curve. Note that on cooling, there's an exotherm that begins at a temperature of about 210 degrees. There's a small bump on cooling that continues and slowly decreases until we hit the eutectic temperature, at which point all of the remaining liquid solidifies. You will also note that on cooling, the temperature that the remaining liquid solidifies is significantly depressed relative to the heating curve, nearly 30 plus degrees below the melting temperature that you'd expect for this alloy. Once again, these DSC experiments are carried out for all of the 6 known samples in this experiment. And the DSC data is being provided as well in the form of Excel files for this lab report. Now we will discuss the various topics that you should be discussing in your report. We will begin by discussing the results from just the cooling curve thermal analysis portion. Number 1, what differences did you observe in each of the cooling curve plots, and explain your observations? 2, how did the pure element thermal curves compare to the other compositions? Compare specifically to the eutectic composition. Explain the meaning of the heat of fusion. How does it reveal itself in the cooling curves of each sample? 4, what is the composition of A, the first solid to form upon cooling, and B, the last liquid to solidify? 5, from the phase diagram provided, estimate the following for each composition: the amount of pro-eutectic phase and the amount of eutectic phase present. Lastly, for each composition tested, provide a small sketch of what you think the microstructure of the material would look like as observed through an optical microscope of each composition for a polished and etched sample. Now we will discuss the aspects of the report related to the DSC analysis, as well as combining the analysis of the cooling curves with the DSC runs, as well as interpreting their results relative to the phase diagram. To begin, provide a table in the report showing the following: the composition of the alloys used in the experiment, ordered by increasing tin content. Include the onset and end temperatures for each peak that you observe in each composition of the DSC runs. Note how many peaks are present in each run that you're able to identify for both the heating and cooling portions of the curves. Indicate whether they're on the heating and cooling portions. Then, looking at the phase diagram and using both cooling curves, the one from the first series of solidification experiments and the cooling curves from the DSC results, explain how they're interrelated. Explain any common features between the cooling curves of the solidification run and the cooling curves of the DSC runs. Relate the results to the lead-tin phase diagram. Do the transition temperatures match those from the phase diagram? If yes, explain why they should, and if not, explain why they don't. The expectation is that you're going to pull together two different sets of experimental data along with a well-known, highly established phase diagram, and explain the experimental results, the limitations of the experiments, and how they correlate to the phase diagram data. The end. Good luck.